Hello and welcome to my YouTube channel. Today we shall be discussing on the topic set theory. Definition. A set is a collection of well-defined or distinct objects. Each of these distinct objects in a set is called an element or a member of the set. Examples of sets include the following. 1. The set of all letters of the alphabet. Now, the letters of the alphabet include A, B, C, D, E, F, and so on up to Z. So, we represent sets using capital letters. So, we may write that let capital A equal to A, B, C up to Z be the set of all letters of the alphabet. So use capital letters here to represent that set. You could use A, it could be B, C, or capital D. Now, this element, or this A, B, C, D, E, F up to Z are called elements of set A. And this element of set A, or members of set A, are separated using commas. So the elements of a set are separated using commas. And all these elements are enclosed using what we call a curly brace. So now this specifies a set completely. So we say that the set of all letters of the alphabet is capital A equal to A, B, C, D, E, F, G, H up to letter Z. Now, since A is a member of this, since small a is a member of set A, we will write in set notation that A, small a, is a member of capital set A. Likewise, we can write that B is a member of set A. We can also write that Z is a member of set A. Small z here if you want, of set A. So, now you see that in this set, 1 is not a member of this set because we have defined a set to be a collection of well-defined or distinct objects. So 1 is not a member of this set because 1 is not in the set of all letters of the alphabet. Since 1 is not in this set, we will write that 1 is not a member of set A. Another example of a set includes the set of even integers. Now, if we denote the set of even integers with the capital letter M. Now, even integers include 2, 4, 6, 8, 10, and so on. So 2 is a member of set M, 4 is a member of set M, 10 is a member of set M, and indeed every even integer is a member of set M. So we separate these members or elements of set M using commas and enclose all the elements using what we call a curly brace. So we'll say that 2 is an element of set M. We'll say that 10 is an element of set M. We'll say that 20, an even integer, is an element of set M. However, 21 is not an even integer. Therefore, 21 cannot be a member of set M. I would write that 21 is not a member of set M. Methods of specifying sets. We have two methods of specifying sets, which include 1, the listing or roster method, which we have just done, and 2, the set builder method. Let's take examples. Number 1, we have a set here, set A, with elements or members 2, 3, 4, 5, and 7. Now, in this set A, we have just listed the members of the set. So this method of specifying a set is called the listing method, or you can also call it the roster method. The second method of specifying a set is the set builder method. Now, in set builder method, we have our set specified in this manner. Now, this is B. So we say that this is set B, which is the set of all x. This column means such that x, that means the element of set B, x, is an even number. And X lies between 0 and 12. So this method of specifying sets describes the nature of the elements or members of the particular set, and from that description we are able to write out or to list out the elements of such a set. Now in example 2, X is an even number, and we know even numbers to include 2, 4, 6, 8, and so on and so forth. But in addition, we are told that the even numbers of set B must be between 0 and 12. So if we attempt to write out the elements of set B, they would be that B will have the following elements. Since the elements lie between 0 and 12, the first element there will be 0, since 0 is inclusive. 0, 2, 4, 6, 8, 10, and 12 is also what? Inclusive. So this method of specifying a set is called the set builder method. Another example of a set builder method is if we have a set, say C, as a set of all x such that x squared is equal to 4. So once again, the set here C has been described, that C is a set of all x such that the square of x is equal to 4. So from this statement, we will be able to get the elements that make up set C. So we pick out x squared equal to 4 and solve. If we take the square on both sides here, we'll see that x is equal to plus or minus 2. So this implies that the elements of set C are minus 2 and 2. So we call this the set builder method. Definition: Singleton set. A set having only one element is called singleton. Examples: number 1, the set A has element 1. So the only member that makes up set A is 1. Since set A is made up of just one element, set A is called a singleton set. Another example is set B. Set B is described here using the set builder method. That set M is equal to the set of all x such that x plus 1 is equal to 0. So if we solve out what we have in this set, x plus 1 equal to 0, this would imply that x is equal to what? Minus 1. So if we write out the elements of set M, we are going to have set M is equal to minus 1, and minus 1 will be the only element of set M. So set M is also called a singleton set. Definition: subset. A subset or a set A is a subset of a set B denoted by this symbol A subset of B, or B contains A, if every element in set A is also an element in set B. So in set language, we write it this way. We say A is a subset, set A is a subset of set B if an element X in A will imply that the same element X is in B. So I shall illustrate this with an example. So here, set A has the following elements: 1, 2, and 3. And set B has the elements 2, 3, 1, 4, and 5. Now we observe here that all the elements in set A are in set B. Set A has the element 1, and 1 is also found in set B. Set A has the element 2, and 2 is also found in set B. Set A has the element 3, and 3 is also found in set B. And of course, in set theory, the arrangement of elements is not important. In other words, if we write the elements 1, 2, 3, it is the same thing as writing 2, 3, 1 or 3, 1, 2, however. But we observe that all the elements in set A are elements also in set B. So we say that set A is a subset of set B. Or we say that set B contains set A. However, we also observe that apart from the elements of set A all being in set B, there are certain elements in set B that are not in set A. So in set A, 1, 2, 3 are in set B, 1, 2, and 3. But there are two elements in set B, 4 and 5, that cannot be found in set A. Since set B contains some elements, in this case 2 elements, that are not found in set A, it therefore implies that set A is not just a subset of set B, but we say that set A is a proper subset of set B. And we write that as set A is a proper subset of B, or set B contains set A, properly. So the difference there is that here implies that set A is in set B, and of course it could also be equal. But the proper sense of it implies that there are certain elements, at least one element in set B, that cannot be found in set A. And in this example, like I said earlier, we have 2 elements, 4 and 5, which can be found in set B, but cannot be found in set A. So set A is not only a subset of set B, but a proper subset of B. Equality of sets. 2 sets A and B are said to be equal if they both have the same elements. We denote this by writing set A equal to set B. So in set notation, set A equal to set B if X an element of A implies that that same X is an element of B. And of course, if X is an element of B, it also implies that X is an element of set A. For example, we have that set M has the elements 4, 8, and 2. And set N has the element 2, 8, and 4. Of course, 4, 8, 2, and 2, 8, 4 are the same sets. Since set M and set N have the same elements, 4, 8, and 2, we say that set M and set N are equal sets, and we write M equal N. So M and N are equal. Empty or null set. This is a set that contains no element. It is denoted by the symbol phi or an empty brace. Please, we should take note at this point. To denote an empty set, you only use one of these symbols. We don't write this, a common mistake students make. They write this to mean empty set. That is not correct. If you write this, this will mean a singleton set. A set with one element, and the element now is phi. So an empty set or a null set is a set that has no element. Let me give an example of an empty set. The set of all integers that are even and odd is an empty set, because an integer is either even or odd. So if you are now asked for the set of integers that are both even and odd, there are no such integers, so such a set would be empty. So if we use capital M to denote such a set, we say that capital M is equal to phi. That means it's empty. Or we write that capital M is equal to, we write our curly brace, and there will be nothing inside. Since all integers are either even or odd, we have no such integers that are both even and odd. So capital M is an empty or a null set. Finite sets. A set is called finite if all its elements can be listed. Example, set A has the elements 2, 3, 4, 5. So here we can easily see that this set A has 1, 2, 3, 4 elements, and we can list them out, 2, 3, 4, 5. So when you are able to list out and know how many elements are in a certain set, such a set is said to be a finite set. And of course, if the elements cannot be listed or counted, such a set will be called an infinite set. Example number 2, we have that set A is given to us in a set builder method. That set A is a set of all x such that 0 is less than x and x is less than or equal to 9. And this simply means that the element of set A lies between 0 and 9. Of course, 0 is not inclusive because this sign here is strict. So if we were to list out the elements of set A here, what would they be? Set A would have the following elements: 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we have been able to list out the elements of set A. Therefore, set A is called a finite set. So if we write set A to be, for example, the set of all integers, such a set will be an infinite set. Why is it so? Because we cannot list out all the integers we have in this world. So we have some negative integers, and then we have some positive integers, 2, 3, we have 4, we have 5, and it goes on and on. So such a set is called an infinite set because we cannot list out all the elements of such set A. So how do we know that a set is infinite? In that set, we'll see 3 dots, 1, 2, and 3, either at the end of the set or at the beginning, sometimes at both ends. So if you see a set like this, is set B equal to, say, 1, 2, 3, then 3 dots, 1, 2, and 3. These 3 dots signifies that the set B has elements that go on and cannot be listed to the end. So set B is called an infinite set. Cardinality of a set. The cardinality of a set, say A, denoted by A within 2 straight bars or small n and A in bracket, refers to the number of elements in set A. So look at the example above, where set A has elements 2, 3, 4, and 5. We can count how many elements are in set A. 1, 2, 3, 4. Set A has 4 elements. So we say that set A has cardinality of 5. So we write that the cardinal number of set A is equal to 4, rather. 1, 2, 3, 4 elements. Or you say n of A is equal to 4. Same thing for the other, for example, number 2. Set A has the elements 1, 2, 3, 4, 5, 6, 7, 8, 9. So let us count how many there are. 1, 2, 3, 4, 5, 6, 7, 8, 9. Set A has a total of 9 elements. So the cardinality of set A here again is equal to 9. Or n of A of this set is equal to what? 9. Because there are 9 elements in that set. So how about the cardinality of a set that is infinite? For example, set B that has elements 1, 2, 3, and it goes on and on. Because we are not able to list out all the elements of set B, we'll say that the cardinality of set B is simply what? Infinity. Or we say that n of set B is equal to infinity. Because we are not able to ascertain how many elements exactly are in set B. Universal set. The universal set, denoted by capital letter U or capital letter E or this symbol mu, is the larger set that contains all the subsets or all the sets being discussed. For example, let U, universal set, be equal to capital Z. What is Z? This is a set of all integers. Set of all integers. Which is equal to, of course, it's an infinite set I explained earlier, and then we have the following elements: minus 5, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, and of course it goes on and on. This is set of all integers. Now we have 4 sets, subsets here. Set A with elements 2, 4, 6, 12. Set B with elements minus 1, 1, 3, 7, 9. Set C has the following elements, and set D has all these elements. Now you observe that all the elements of set A, 2, 4, 6, 12, are in set Z, in this big set Z, because these are all integers. And since the U, which is Z, is a set of all integers, then 1, 2, 3, 4 integers of set A are all in Z. Same thing for set B. Set B also has all integers, minus 1, 1, 3, 7, 9. And these integers of set B can also be found in capital Z. Set C has the integers also, and all these integers can also be found in Z. And set D, 1, 2, 7, can also be found in set Z. It is safe to say that set A is a subset of set U, and set B is a subset also of set U. Set C and set D are also subsets of set U respectively. So set U is the larger set that contains all of set A, set B, set C, and set D. These are the sets under consideration. So this larger set U is what we refer to as the universal set. So it is a set that contains all other subsets under consideration. Power set. Let A be a set. The power set of A is denoted by P and then A in bracket and defined as the set of all subsets of set A. If set A is a finite set with n number of elements, then the power set of A contains 2 raised to power n elements. For instance, if set A has the following elements, small a and small b, so there are two elements in set A. So here our n is 2. So n here refers to the number of elements in the particular set. So set A has 2 elements. So we want to now know the first, number 1, how many subsets will set A have? In other words, how many sets will be in the power set of A? So what do? We now write 2 raised to power n. Since our n is 2, this simply means 2 raised to power 2 equal to what? 4. So this means that the power set of A will have 4 subsets in it. Now the point I want to make here is this. Take note of this. The empty set and the entire set itself are automatic members of the power set of every set. So for every set, the empty set and the set itself are already automatic members of the power set. So set A will have 4 members as its power set. So let us see. Power set of A include the following. The first member of the power set is the empty set. The second member, an automatic member also of the power set, is the entire set itself, A. And what is set A? Set A is AB. So A and B. These are the 2 members of the power set that are automatic. So we've taken 2 out of 4. 2 are left. We have A and B. The next subset there is A. And the next one is what? B. So the power set of set A has the following sets: the empty set, the entire set, set A, and set B, or subset A. So we say that the power set is what? The set that contains all subsets. Example 2. Set B has elements 1, 2, 3. So here n is equal to 3, since there are 3 elements in set B. So the power set of set B will contain 2 raised to power n elements, or subsets. Since n is 3, this means 2 raised to power 3, and that is equal to 8. So set B, so the power set of set B will have 8 subsets. And we should remember that the empty set and the set itself are automatic members of the power set. So the power set of set B will contain the following elements or subsets. The first is the empty set. The next is the entire set itself, set B. And what is set B? Set B is 1, 2, and 3. So out of 8, we've taken 2, the 2 automatic ones. 6 are left. We'll now break them up. The next one there is 1. The next one is 2. The next one is 3. The next one is 1 and 2. And the next one is 1 and 3. Let's count. 1, 2, 3, 4, 5, 6, 7. It's left with 1, and the last one will be 2, 3. So these are all the possible subsets of set B. And we call this collection here the power set of B. Operations with sets. 1. Union of sets. The union of any 2 sets, A and B, is the set of elements that belong to set A or set B. It is denoted as A union B. This symbol is like a cup. It's like a U, a cup. A union B. So in set notation, we say that A union B is equal to the set of all elements X such that X belongs to A or X belongs to B. I'd like to emphasize at this point the usage of, of OR. Now, OR is used here in the inclusive sense. Now, normally, when OR is used in English language, it's used in the exclusive sense. What do I mean? Now, in English language, if we say bread or butter, you should choose. It would mean that you should either take bread or you take butter, which means if you take bread, you cannot take butter. And if you take butter, you cannot take bread. So when OR is used in this manner, it is used in the exclusive sense. However, in mathematics and in set theory in particular, when we use OR, we use it in the inclusive sense. So what would it mean here? Bread or butter in the inclusive sense would mean that you could take bread without butter, or take butter without bread, or you can take bread and butter. So I like us to keep in mind, this exclusive sense of OR that is being used in set theory. So, examples, to illustrate what union of set means. So let A be the set with elements 1, 3, 5, B with elements 3, 5, 8, and set C with elements 2, 4, 6, 8. We want to establish the following. 1. A union B. 2. A union C. 3. A union B union C. So number 1, A union B. All the elements in set A are 1, 3, and 5. OR is inclusive, remember? So we now add up the elements in set B. And what are the elements in set B? 3, 5, and 8. But 3 is already in set A. And in set theory, repetition of elements is not allowed. So since we already have 3 in set A, we cannot write 3 again. We already have 5 also in set A. We cannot repeat 5 the second time. So what is left now is to add up what? 8. So in other words, you see that the union of set A and set B is simply the collection of all the elements in set A and set B without repetition. Similarly, the second one, A union C. So the elements of set A again are 1, 3, and 5. We now add up the elements of set C, which are 2, 4, 6, and 8. And they are not here, so we put them down. 2, 4, 6, and 8. So again, the union of set A and set C is simply the collection of all the elements or members that make up set A and set C without what? Repetition. And of course, you can do the same thing for the third one, which is A union B union C. So this simply means we should put together all the elements of set A, set B, and set C. And the key word there is that you must do that without repetition. So elements of set A are 1, 3, and 5. Of set B are 3, 5, and 8. But 3 and 5 are here already, so we only write 8. Elements of set C are 2, 4, 6, 8. So 8 is here already. There is no 4, there is no 6, there is no 2. We now add up 2, 4, and 6. So this now becomes the union of set A, set B, and set C. Intersection of sets. The intersection of two sets, A and B, is a set of those elements X such that X belongs to both A and B. It is denoted as A and then with this stylish N, B. So this means A intersection B. So in set language, we write that A intersection B is equal to the set of all X such that X, the element X, belongs to set A and the same element X belongs to set B. In other words, the intersection of two sets is simply the collection of the elements that are common to both set A and B. We'll take a few examples to illustrate what this means. Example, let set A have the following elements 1, 3, 5, 8, set B 3, 5, 7, and set C. So we want to find the following: A intersection B, and then A intersection C, and so on and so forth. So number 1, A intersection B. So we now check. The elements in set A are 1, 3, 5, 8. Those in set B are 3, 5, 7. We now pick out the element we can find in both sets. We find there is 1 in set A, there is no 1 in set B. So 1 cannot be in the intersection. There is 3 in set A and there is also 3 in set B. So the element 3 is in the intersection. There is 5 in set A, there is also 5 in set B. So 5 is also inclusive. There is 8 in set A, there is no 8 in set B. There is 7 in set B, there is no 7 in set A. So the elements 3 and 5 are the only elements that can be found in the intersection of set A and B. The second one, A intersection C. So the elements of A are 1, 3, 5, 8. Of C are 2, 4, 6, 8. So there is 8 in both A and C. And what else? I can't see any other thing. So A intersection C is 8. And that's a singleton set. The third one, I. B intersection C. The elements you can find in set B and set C. Set B, 3, 5, 7. Set C, 2, 4, 6, 8. Nothing in common. So the intersection of set B and C is empty. So we write that B intersection C, we write our curly brace open, or we write B intersection C is equal to, we write the symbol phi. So this would mean that there is no element that can be found in set B and set C at the same time, or there is no common element between set B and C. And of course the last one is B intersection A union C. So bracket first, we'll deal with the bracket first. So A union C. A union C means all the elements in set A and set C without repetition. So set A has the element 1, 3, 5, and 8. Set C has the element 2, 4, 6, 8. 2, 4, 6, 8. We can't bring in 8 again because there's 8 already. And remember that repetition is not allowed when listing elements in set. So we have the bracket handled. A union C has the following elements. We now want to bring in B and its intersection. So B intersection A union C is equal to, what is B? B is 3, 5, 7. And then A union C, 1, 3, 5, 8, 2, 4, 6. So what are the elements we can find in B and also find in A union C? There is 3 here, there is 3 here. I can find 3. There is 5 here, there is 5 here. There is 7, there is no 7. So the only 2 elements that can be found in both sets, that is set B and set A union C, are 3, 5. So this now becomes B intersection A union C. Complement of a set. Given that A is a set, the complement of set A, denoted by A prime or A with a small power C, is defined as the set consisting of all elements in the universal set U or E that are not in set A. So in set language, we write that A complement, or A prime if you like, is still A complement, is equal to the set of all elements X, such that those elements X are in the universal set and the element X is not in the subset A in question. With an example, we'll understand better what we are trying to say. So example, if the universal set U has the element 1, 2, 3, 4, 5, 6, 7, 8, and 9, and A is a subset of this universal set with the element 1, 3, 5, 7, and 9. Of course, A is a subset of U. We want to find the following: 1, A complement; 2, A complement union A; 3, A complement all complement; and 4, A complement intersection A. So let's go ahead with it. The first one is A complement, A prime, of course, or A complement. This simply means the set of all the elements that can be found in the universal set U and cannot be found in set A. So set A has elements 1, 3, 5, 7, and 9. So there is 1 in set U and in the universal set, and there is 1 here also. There is 2 in U, but there is no 2 in A. So 2 is there. There is 3 in U, there is 3 here. There is 4 in the universal set, there is no 4 here. There is 5 here, there is 5. There is 6 here, there is no 6 here, 6. There is 7 here, there is 7. There is 8, there is no 8. I write 8. There is 9 and there is 9. So I stop. So these elements 2, 4, 6 and 8 now form what you call the complement of set A. Remember, the definition says that the complement of set A is what the set of all elements that are in the universal set but are not in set A. So these elements 2, 4, 6, 8 are in U. Let's see, 2, 4, 6, 8 are in U, but none of these elements is in the subset A. So this forms what you call the complement of set A. So 2, 4, 6, 8 is a complement. I want to now find a complement union A. So what is a complement? A complement is 2, 4, 6, 8. Union A means you should combine the elements of a complement as well as what A. So we're going to write them down without repetition. So the elements of a complement are 2, 4, 6, 8. So 2, 4, 6, 8. We now combine those of set A. Set A has elements 1, 3, 5, 7, 9. So we now add up 1, 3, 5, 7, and 9. And what do you observe? You observe that when you take the union of a complement with A, what you get is simply the universal set U. The elements 2, 4, 6, 8, 1, 3, 5, 7, 9 are here. 2, 4, 6, 8, 5, 1, 3, 5, 7, 9. They are all here. So the union of a complement with A is simply equal to what? The universal set. And of course, that makes a lot of sense. The third thing we want to establish is a complement or complement. So what do we know? We already know a complement. What is a complement? A complement is 2, 4, 6, 8. That is a complement. So we want to now take the complement of that complement. So we are taking the complement of this. And what does that mean? This simply means all the elements in the universal set that are not in a complement. So what are they? 1 is here. There is no 1 here. There is 2 in U. There is 2 here. There is 3 in U. There is no 3 here. 3. There is 4 in U. There is 4. There is 5 in U. There is no 5 in a complement. So 5. There is 6 in U. There is 6 here. There is 7 in U. There is no 7 here. So 7. There is 8 here. There is 8. There is 9 in U. And there is no 9 here. So 9. So this now forms the complement of a complement. Recall, a complement is 2, 4, 6, 8. We now take the complement of this set, which means the elements in the universal set that are not in this set, which is a complement. And that gives us 1, 3, 5, 7, and 9. And of course, the last one there is a complement intersection A. What is a complement? A complement is 2, 4, 6, 8. Intersection A. What is A? 1. A is 1, 3, 5, 7, and 9. So what are the elements? We are taking intersection, which means the elements that are common to both sets. So what are the elements that can be found in a complement? And those elements can also be found in A. Let us see. A complement 2, 4, 6, 8. A 1, 3, 5, 7, 9. No element in common. So a complement intersection A is an empty set, or phi empty. So what can we see from here? We see that the intersection of the complement of a set with the set itself is always an empty set, while the union of the complement of a set with itself is always the universal set. And of course, these are very important results in the theory of sets. Difference of two sets. Given two sets A and B, their difference is given by A minus B or B minus A. Now A minus B means elements of set A which are not in set B, while B minus A means elements of set B which are not in set A. In other words, A minus B or A backslash B, they mean the same thing, is equal to the set of all elements x such that x belongs to set A and x does not belong to set B. While B minus A or B backslash A, this means B, the difference of B and A, is equal to the set of all x such that x belongs to set B and x does not belong to set A. So we'll take an example very quickly, to illustrate what this really means. Example, if set A has the following elements, A, B, C, D, E, F, set B has the elements B, E, F, and H, then what will be A minus B, or the difference of A and B, and B, what will now be the difference between B and A. So the difference between A and B, or A minus B, simply is what? Let's go back here. The set of all elements in X such that X is in A and X is not in B. So A minus B means the elements we can find here in A and cannot find them in B. Let us check. There's A in a small a here. Is there small a here? There's no small a here. So small a is a member. There is B here. Is there B here? Yes, there is B. So B cannot be here. We want only elements that can be found in A and cannot be found, in set B. We now check again. C is in A. Is there C here? No, there's no C. We write down C. D is in set A. Is there D here? There is no D here. We write down D. There's E in A. Is there E here? Yes, there is E here. We cannot write E. We now go to F. F is here. Is there F here? There is F. We cannot write F. So we stop there. So A, the difference of A and B is the element 1, A, C, and D. We can also write this as A backslash B. This is the set of all elements that can be found in set A but cannot be found in set B. So ACD can be found in set A, and these three elements cannot be found in set B. So A, C, and D are not here. So this now forms what we call the difference of set A and B. So which is A minus B, or A backslash B. The other one is B minus A. The set of all elements, B minus A, such that those elements are in set B and the same elements are not in set A. So let's check them out. Go to set B. There is B here. Is there B here? There is B. So we cannot put B here. There is E here. Is there E here? Yes, there is E. We can't put E down. There is F here. Is there F here? Yes, there is F. We cannot put F down. There is H in B. Is there H here? No, no H. We put down H. And that is it. So B minus A, the set of all elements in set B that cannot be found in set A. So H is in set B and there is no H in set A. So the difference of B and A, which is B minus A, is a singleton set with element what? H. This can also be written as what? B backslash A. Symmetric difference. The symmetric difference of set A with respect to set B is the set of elements which are either in A or B, but not in their intersection. This is denoted as A with a small triangle here, B, or A symmetric difference B, or A symmetric difference B. There are three symbols here which can be used. In set notation, we say that the symmetric difference of set A and B is a set of all elements X such that X is an element of set A, or X is an element of set B. Remember, the or here is inclusive, and X is not an element of A intersection B. This definition is equivalent to saying that the symmetric difference of set A and B is equal to the union of set A and B minus the intersection of set A and B. Let's take an example. Given that set A has the elements A, B, C, and set B has the elements A, E, F, and G, then what is the symmetric difference of set A and B? This is how we do it. Just take first the intersection of set A and B. So what can we find in set A and can also find in set B. What are they? There is A here, there is A, so A is there. There is B here, there is no B. There is C here, there is no C. So the intersection of A and B is a singleton set A. So the symmetric difference of A and B is everything in A and B except A. So that would be B, comma C, then E, F, and G. That's all. So what is this? This is simply the union of A and B minus the intersection of A and B. So we take the intersection of A and B first, which is a singleton set A, because this element A is found in set A and is also found in set B. This is the only element we do not need in the symmetric difference of A and B. So we take the intersection of A and B out and write down all other elements that are left. So symmetric difference of A and B is a set with elements B, C, E, F, and G. Venn diagrams. Now sometimes information involving set theory are represented on Venn diagrams. And on those Venn diagrams we can easily solve problems that involve sets. So in a Venn diagram, the universal set U is represented by a large rectangle like this that represents the universal set, and we'll just write here U, and other sets which are subset, of course, are represented by what? Circles or just oval shapes like this. So this is what we call a Venn diagram. The rectangle represents the universal set, and the small circles inside will represent what? The subsets. So this diagram we're going to use to interpret some of the definitions we had earlier taken in this course. So let's take some definitions and represent them on Venn diagrams. So the first one to check is A intersection B. So we draw the first subset, we call it subset A. We draw the next subset, subset B. And if you observe, you see that those two subsets intersect each other. So this rectangle is U, our universal set. So what then is the portion that is A intersection B on this Venn diagram? Let us see. Then you observe that these two subsets A and B both meet at this point where I have shaded. So this shaded region represents the point of intersection of set A and set B. So this region is what we call the region that represents A intersection B. Next, we want to represent A union B on a Venn diagram. So our first subset A, the next subset here is B, and both subsets are to be enclosed within a rectangular shape, which is the universal set U. So we want to shade the portion that represents the union of A and B. So what's A union B? Remember, A union B simply means the set of all elements in set A and set B without repetition. So A union B will simply mean the set of all elements in set A, of course, and in set B. So the shaded region here will represent the union of set A and set B. So the next one we want to look at is A difference B. So for A difference B, we draw again. That represents A, and this represents subset B. And of course, again, they are both enclosed within the rectangular universal set U. So if you recall what A union B is, we had said that A union B, A difference B rather, beg your pardon, is equal to what? The set of all elements X, such that X belongs to A and X does not belong to B, if you recall a while ago. So the difference between offset A and B is the collection of all elements in set A. Elements in set A which do not belong to set B. So you observe that the shaded portion here contains only elements in set A, which do not belong to set B. Now, if you shade this intersection, you are wrong, because the elements in the intersection belong to set A and set B. And A difference B is saying that you take only elements that belong to set A, and those elements are not in set B. So A minus B, or A difference B, will exclude elements in the intersection of A and B. Similarly, the difference between B and A would be, so this is set A, my diagram is not too fine, set B. So we enclose them within the universal set U. So again, B minus A is a set of all elements X such that those elements are in set B and those same elements are not in set A. So the difference between set B and A would now be the following elements. Elements that are in set B, the shaded portion, and those elements are not in set A. So the elements are not in set A, and of course they cannot be here also, because this portion contains elements that are both in set A and set B. So this will represent, B difference A. Let's now look at how to represent the symmetric difference of set A and set B on a Venn diagram also. So our two subsets A and the overlapping subset B, both subsets are within the universal set because they cannot live there, U. So if you recall what our symmetric difference of A and B is, I simply said that the symmetric difference of set A and B is simply the collection of all elements in set A and B except those found in the intersection of set A and set B. So set A and set B intersect in this region. That's the intersection of set A and B. So the symmetric difference of set A and B is simply the collection of all the elements in set A and all the elements in set B except those found in the intersection of set A and set B. So this Venn diagram would represent the symmetric difference A, symmetric difference what? B. The symmetric difference between set A and set B. Collection of all elements in set A and set B except those found in the intersection of set A and set B. Cartesian product of sets. A Cartesian product of two non-empty sets is the collection of all ordered pairs, keywords, obtained by the product of two sets. Given two non-empty sets, A and B, their Cartesian product is denoted by A times B and defined by A cross B, or the Cartesian product of A and B, is equal to the set of all ordered pairs such that A belongs to set A and B belongs to set B. So this definition is what we refer to as the Cartesian product. Now I must emphasize something here in the definition, the word ordered pairs. So let's explain this a bit. Now if you have a certain pair, say 2, 3, this is a pair 2 and 3. If this pair is called ordered, if the word ordered is attached to this pair, what it means is this. It would mean that the order of these numbers 2 and 3 cannot be altered. In other words, this pair cannot be written as 3, 2. So ordered, in the sense that the first element in this pair must be 2 and the second element in this pair must be 3. So if you write this pair as 3, 2, you are now making the first element 3 and the second element 2. In that case, the order of the pairing has been altered. Hence, it's no longer an ordered pair. So that is the definition. That is what we mean when we say that this is an ordered pair. So back to the definition. A times B, which we call the Cartesian product of set A and B, is the set of all ordered pairs. So this product gives us pairs at all times, such that the first element of that pair must come from the first set A. And the second element of that pair must come from the second set what? B. So by the time when we are able to list out all of such pairs or any of such pairs, we say that we have the Cartesian product of set A and set B. So we'll take one or two examples now to illustrate. For example, if A is a set with elements 1, 2, B is a set with elements 2, 3, and 4. Question is, you should find A times B, and this means you should find the Cartesian product, of set A and B. And what is this? The collection of all other pairs, of between set A and B. So, solution. The Cartesian product of A and B, which we write as A times B, we said is a collection of all other pairs. What will be our first pair? If we take 1, 2, that would be an ordered pair. How? Let's see. Number 1, this is a pair. There are two numbers in this bracket. But the first element in this pair, which is 1, belongs to the first set A. And the second element in this pair 2 belongs to the second set B. That is what the definition is saying here. That the Cartesian product is a set of all ordered pairs such that the first, element of the pair is an element of the first set A, and the second element of that pair is an element of the second set what? B. So the pair 1, 2 would be an ordered pair. Another pair we could find here is 1 and 3. 1 and 3. Because 1, the first entry, belongs to the first set, and the second entry 3 belongs to what? The second set. So what we are saying in essence is, if you write this pair, the first pair, instead of 1, 2, you write 2, 1. This would be a wrong pair, because the pair is not ordered. The first element here 2 belongs to the second set B, and the second element 1 belongs to the first set A. And the definition of Cartesian product requires that the first element of this pair must come from the first set, and the second element of this pair must come from the second set. So the pair 2, 1 or 3, 1 would be a wrong pair. So 1, 2, that is 1 and this 2, that's the first pair. Another pair is 1, 3. I can see another pair here, 1 and 4 is another pair, because 1 belongs to the first set and 4 belongs to the second set. I can see another pair here, 2 and 2, 2, 2. Here the first 2 belongs to the first set and the second 2 belongs to the second set. The next pair I can find here is 2 and 3. 2 belongs to the first set A and 3 belongs to the second set B. I can find another pair here, 2 and 4. And 2 belongs to the first set A and 4 belongs to the second set B. So this is a collection of all the possible ordered pairs between set A and set B. So we call this the Cartesian product of set A and set B. So the last example for today is, if A is a set with elements 1, 2, B another set with elements A, B, C another set with elements 3 and 4. Want to find the following: A cross B, or the Cartesian product of A and B, the Cartesian product of B and C, and of course the intersection of both Cartesian products. So A times B, or the Cartesian product of A and B, is equal to what? The set of all ordered pairs, of set A and B. So 1, A is the first ordered pair that I see. The next one is 1, B is the next ordered pair. The next ordered pair is 2, A, and the next ordered pair is 2, B. So these are the ordered pairs, or this is the Cartesian product, of A and B. So that is question number I. So question number II, we need the Cartesian product of B and C. So that would be the set of all ordered pairs between B and C. So the first one I see here is A and 3. A3 is the first one. I see A and 4. A and 4. I see B and 3. B, 3. I also see what? B and 4. I see B and 4. So this is a Cartesian product, of B, set B and C. So I requires us to take the Cartesian product of A and B intersection the Cartesian product of B and C. So we have, this Cartesian product and this also, and we are now asked to get the intersection. So the Cartesian product of A and B is the following here: 1A, 1B, 2A, 2B. While that of B and C is A3, A4, B3, and B4. We now seek the intersection. What's intersection? We want to now check between these two, Cartesian products. Do we have any pair in common? We check. There is 1A here. There is no 1A. There is 1B here. There is no 1B here. There is 2A here. There is no 2A here. There is 2B here. There is no 2B here. We now check the other way around. There is A3 here. There is no A3. There is A4, no A4. There is B3, no B3 here. And lastly, there is B4 here, and there is no B4 here. So we see clearly that the intersection of the Cartesian product of AB and that of B and C is an empty set. So we say that this intersection is phi, which is empty. Or we say that this intersection is simply an empty brace. So this would mean that the intersection of this Cartesian product is an empty set, since we can't find any pair, in common between the two Cartesian products. Please don't forget to like, subscribe, and leave a comment on this video. Thank you, and bye-bye.